Hello. 21.4 is all about Lenz's law. Lenz's law is presented in the book this way. The current or EMF that is induced by a changing flux is in the direction as to oppose the change in flux. Likewise, the current or EMF that is induced by a conductor moving in a magnetic field is in the direction such as to oppose the conductor's motion. That's how it's presented in the book. I find that explanation quite confusing. First off, it's talking about current or EMF, both kind of interchangeably with direction, and that seems confusing to me. It also really mixes two ideas in this definition. So I'm going to write out a couple different definitions for you to try to untangle or unwind this one, okay? So as I mentioned, I'm going to give you a few better definitions maybe. So this is chapter 21.4, and it's all about Lenz's law. And Lenz's law in general was the negative sign in front of Faraday's law, which is strange, but really what Lenz's law does is it gives the direction of the induced current in a conductor due to a changing magnetic flux. It also, if you don't want to talk about the direction of the induced current, the way that it should have been said is that it gives the sign on the induced EMF. Or the induced voltage. Another definition that is often used is, so this would be another way to write Lenz's law, and that is, the second definition reads that for an induced voltage, the corresponding induced current will be such that its B field opposes the motion that induced it. And then I crossed out motion and put change in magnetic flux. An even simpler way to say it would be that the induced current will always oppose the change in motion that induced it. Another, and probably my favorite definition for Lenz's law is given by a pretty famous E&M author known by with the name of Griffiths. But his way of writing Lenz's law was my favorite, and that is that nature abhors a change in magnetic flux. That's my favorite. So I think the best way to really dive into what this is to remind you that this is really just giving the direction of the induced current that is caused by a changing magnetic flux in an area of a conductor or in a wire loop. That really is all Lenz's law gives us, and that's why it's the negative sign in front of Faraday's law. So if you remember, this is nature hating a change in magnetic flux, so it opposes it. It always is negative of the change in magnetic flux. And so we're going to revisit that example that we've seen two other times now with the aluminum ring falling through a uniform B field. Only this time we're going to determine the induced current's direction inside of that loop of wire that's falling into the B field. So we're going back to our example, and this will be the aluminum rod aluminum ring falling through a uniform B field as shown. This time we're going to determine the direction of the induced current inside the conductor in 3 or 4 different positions. So we're going to say determine the induced current's direction in the specified places. So we'll be relying on a picture again. So I'll show the picture. And so we'll have our uniform magnetic field directed into the page. We can draw our ring in a few places, so we'll have it here, 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 and here. And we can just show the direction of the current with the green marker. So we'll say that this is A, B, C, D, and E. And now to do this, we're going to have to go through kind of a step-by-step thought process here. In order to apply Lenz's law to determine the direction of the induced current, we first have to, so this will be our steps in determining the direction of the induced current. So first we have to decide at all if, or so we'll say, is there a changing magnetic flux? And so if not, no current. 2, how is the flux changing in the area? 3, what B field is required to oppose the change in flux? And 4, what direction of current would create those B field lines? Or we could say would produce, or establish is my favorite, but I'll say I've already written produce the B field from step 3. And so we can work through these steps together now. So we have our coil up here at A, and all of these, you might note to yourself, are going downward. So each coil is falling down with some perhaps accelerating velocity, but we don't really care. We just know that it's moving through this B field like shown. So if we look at the first ring as it falls, it's not inside the B field at all. And so what would A's delta phi be? Well, of course, if there's no B field in there at all, it would have no changing magnetic flux, and so there would be no induced voltage across this loop, so there would be no induced current. So A has none. If we look at B, B is actually starting to enter the B field. So our first question, is there a changing magnetic flux? Well, the answer is yes, there is. Now you have to decide how that magnetic flux is changing. Well, as it falls, would there be more X's in the area or less? So as it falls into this B field, it would be submersed or completely immersed inside of that B field. So the number of X's in the area, the number of B field lines going through the area, would be increasing until, of course, it's all the way inside of the field. So at B, we would have a changing magnetic flux, and the change would be that there would be more X's in the area. Well, nature hates a change in magnetic flux, and so in order to oppose that, it will create its own currents inside that conductor, and those currents are going to be produced in order to create a B field to oppose the change in flux. Okay, so if our area at B is increasing in X's, if the magnetic flux is increasing going into the page, then what B field is required to oppose the increasing X's? Well, we wouldn't want to add more X's, that would only increase more, and so we want to add the opposite of X's. Well, the opposite of arrows going into the page would be arrows coming out of the page. That means when we're looking at the B field that's required to oppose the change in flux for B, we would need the induced currents to add dots, or arrows going out of the center of that loop. Finally, we can figure out what direction the current would have to be to produce the B field from that, what we just decided would be dots. And so this is where we have to use the second right-hand rule. And so here's our first loop, and really you only have two options. If you recall from previous videos, the current can either be established going clockwise or counterclockwise. That's it. So if I point my thumb in the clockwise direction around that loop, my fingers would wrap into the page on the inside of the loop, and that would be adding X's. So we know if we want to add dots, we would have to have a counterclockwise current, because that would add dots into or out of the page. And so for B, we can now finally give the answer that B would have a counterclockwise current induced around the coil or through the coil, like so. And so we could say counterclockwise for our answer for B. Is the magnetic flux changing for C? Now it might look like it's going over 1x, but this represents a uniform B field. So as soon as the loop is fully immersed in the B field, and until it starts to leave the B field, there will be no more change in magnetic flux through the area of the coil, and so C would have none or no induced current because the flux isn't changing. How about for D? So D is leaving the field, so we have to go through these steps one more time. Is the flux changing? Well, of course, if it's leaving the field, it's losing magnetic field lines as it leaves the field. So that means that the flux is changing by the area losing X's. Now we have to decide what B field is required to oppose the change in flux. Well, if we're losing X's, that means we have to add X's. And as we showed when we were analyzing part B, if we have a clockwise current around the loop, it would add X's into the area of the loop. So we know that the direction of the induced current for part D is clockwise. Once the loop leaves the B field completely, then there would be no more change in flux, and so there would be no induced current for part E either. I know that's a lot to take in, but that is Lenz's law in a nutshell. And we'll do several examples using both Lenz's and Faraday's law, and your recitation also uses Lenz's and Faraday's law. I hope everything goes well and smoothly, and make sure you come to office hours if you need help.